Hey folks, another day, another lecture. I have the same shirt on, so you can see I'm just keeping this going. All right, let's get it going. I guess I have to do this whole teaching thing instead of listening to music all day while no one's home. Okay, picking up 14.4, manipulating equilibrium expressions. Okay, so up to this point, we've talked about how the equilibrium expression, or the equilibrium constant rather, is constant. But the value of that constant can change depending on the units that you're using in the reaction, right? We noted that Kc and Kp for the same reaction can have different values because there's different units. Well, as we shall also see, the Kc value can change depending on how you balance the reaction. All right, so notice I've got this reaction written two different ways, okay? One in which the way we would kind of balance this normally. And now in this reaction, I've divided all the stoichiometric coefficients in half. And I know some chemistry instructors say you can never have a fraction for the coefficient. It's perfectly fine because we're not talking about like 1/2 of an N2 molecule. We're talking about 1/2 of a mole of N2 molecules. So halves in these balanced reactions are perfectly fine for me. Okay. So now I'm going to go ahead and write this Kc. I'm going to write the equilibrium expression for the way I've written it up here on the top. All right. And so that's going to be bracket NH3 squared, because I've got the 2, all divided by nitrogen raised to the first power times hydrogen raised to the third power. Okay. And so now I want to point something out. If I were to take the square root of this whole expression, so I'm just going to say raise this to the 1/2 power, what happens? Okay. Well, of course, that means I'm going to get now Kc to the 1/2 power. And so that all equals the following. So NH3 squared to the 1/2 power just becomes NH3. Okay. And now N2 to the 1/2 power becomes N2 to the 1/2 power. I think I repeated myself there. And then now hydrogen becomes H2 to the 3/2 power. Okay. Well, what happens if I were to just write the Kc prime? If I wrote the equilibrium expression for the way I've got this reaction balanced? Well, you might notice already that I'm going to get the same thing that I just wrote down. So now for the second reaction, that's NH3 with no, well, it is to the power 1, right? But we don't have to write to the power 1. And now that's N2 raised to the 1/2 power from that coefficient, and H2 raised to the 3/2 power from that coefficient. Okay, and so you can actually see now that Kc, the square root, so I'll rewrite that just as Kc square root, equals Kc prime. Or I could write that Kc equals Kc prime all squared. And so you might notice now then that we would actually get a different value for the equilibrium constant depending on how we balance the reaction. So it's really important that if we were comparing this reaction to a set of data, maybe somebody gave us a set of data, look, here's the concentrations for this reaction. We would need to specify how we're balancing this reaction. Okay, and so typically we would balance it in this way. That would be more of the standard way. But if we did balance it with these 1/2 integers, that would be fine. We just have to note that that's how it's been balanced. Okay, So now what about, is there like a general rule that we can come up with? And there is, and it's right here, okay? So if a reaction is multiplied by X, and what I mean by multiplying the reaction by X is, for example, to go from this reaction to this reaction, we multiplied it by 1/2, okay? So if a reaction is multiplied by X, the equilibrium expression is raised to the X power, right? So once again, with this example, when we go from this reaction to this reaction, we say times 1/2. However, you notice that for the equilibrium expression, instead of multiplying the equilibrium constant by 1/2, we raised it to the 1/2 power, okay? So now similarly, if a reaction is divided by X, the equilibrium expression is raised to the 1/X power. So another way we could think of this reaction is if instead of saying that we multiplied it by 1/2, we could say that we divided it by 2, right? And so if I divide the reaction coefficients by 2, I'm going to raise the constant to the 1/2 power. So it's all the same, just depends on how you think of it, okay? So now what if we just completely reverse a reaction? So I know we talked about how these equilibrium reactions, there's a forward reaction and there's a reverse reaction, okay? So for example, this generic reaction right here, I could think of A going to B, or I could just completely write that backwards, B going to A. Well, based on this rule right here, what you might notice is if I write this as K forward and I write this as K reverse, you can see, hopefully you can see that they're going to be the inverse of each other, right? So I want to go back to these examples that I showed you guys right here. And this is exactly kind of what we were getting into with this one. So with this H2 plus O2 reaction, you notice, right? Remember, it has this ridiculously huge K value, meaning the position is on the right, okay? Well, if I were to flip this reaction, like I discussed earlier, like if I said, what if we start with H2O? How likely is it that H2O will go backwards into H2 and O2? And the answer is not very likely, because if I were to flip this reaction, then this equilibrium constant becomes 1/10 to the 81, which is a ridiculously small number. And then same with this reaction, right? If I were to flip this reaction and say, what if I start now with 2 COs and O2? Well, now that Kc gets flipped, and that says that when I have CO and O2 together, they will undoubtedly form CO2 and react to completion, okay? So hopefully that makes good sense. And the final thing we'll talk about is with this manipulating K values, what if I have a set of reactions that then ends up getting added together, okay? So for example, we can add these two reactions together to get some total reaction. We will later learn this as a mechanism, so we don't have to worry about this too much right now, but as we progress through the semester, we'll see that chemistry often occurs in steps, okay? So maybe this is like step 1 of our mechanism, and this is step 2 of our mechanism. And so if I were to add these two reactions together, that would give me like the total reaction. So let's do it. Let's add these reactions together. So when I bring this down into plus O2, okay, so we have that there. But now you notice there's an O2 and an O2, okay? So I can now write into gas plus 2O2 gas. Well, what about the two NOs? Well, remember, when I add reactions together, the two NOs and the two NOs will cancel, right? And so now we get a new equilibrium reaction. I'll just call this K total. And so now I have 2 NO2 right there. Okay. So if I were to do the following, so let's write all of these equilibrium expressions down. So K1, for example, is, let's see, NO all squared divided by N2 times O2. Okay, well, what about K2? Well, that's going to be NO2 all squared. And now that's divided by, oops, I was going to look at K total. We're looking at K2. So that's divided by NO squared times O2. Okay, and something cool happens. What if happens if I take K1 times K2? What does that equal? So let's do that. Let's multiply these two things together. And you can see when I multiply these two things together, hopefully you can see that the NO2 squared and the NO2 squared is going to cancel. And the O2 and the O2 is going to combine to make O2 squared. So when I multiply these two expressions together, I'm going to get an NO2 all squared. The NO squared and the NO squared cancels, so that goes away. I have an N2 on the bottom, still raised to the first power. And then now I have an O2 all squared. Okay, well, let's now look at this K total reaction. How would I write an equilibrium expression from this K total reaction? Products over reactants, right? And that would go as NO2 squared divided by N2 times O2 squared. So you can see that that actually equals K total. Okay, so when I combine reactions like this and add them together, so I might be adding the reaction together, but the equilibrium constants and the equilibrium expressions get multiplied together. Okay, so keep these manipulating K expressions straight.